Hello, my name is Kevin Craig. This is a presentation about a disc bar rigid body that moves in plane motion. Here you see a picture
Okay.
of that rigid body. It's a disc with two bars rigidly attached to the disc, one on the front of the disc and one on the back of the disc. The reason for the two bars is so that the rigid body can perform plane motion. It can roll on the horizontal bar. In order for that to happen, there can be no forces acting on the rigid body in and out of the plane of motion. It would cause the rigid body to tip or would cause it to turn as it tries to move on the horizontal bar. For plane motion to happen, there can be no forces acting perpendicular to the plane of motion. And if the plane of motion is this plane that you see here in the picture, which we'll call the XY plane, there can be no forces acting in the Z direction, perpendicular to that plane. Hence, I have a bar in the front, and you can see the bar in the back. This is so that it is balanced and the rigid body can perform plane motion, and I can use plane motion analysis techniques to model, analyze, and predict its motion. How does this actually move when I displace it from its static equilibrium position? Well, the video here will show you that. You can see it oscillates back and forth in a very slow vibration. And our goal here is to try to understand this behavior, be able to predict its behavior, understand the effect of the parameters of the rigid body on its behavior. We have the actual system, we can observe the experiment, we can make measurements on the experiment, so we can validate any predictions we make with our modeling and analysis to determine how well we are modeling and analyzing this rigid body. So this is a disc and bar rigid body moving in plane motion, and we'll define exactly what we mean by plane motion. And we're going to perform a dynamic system investigation. So this is not your typical dynamics problem. This is a dynamic system investigation into a dynamic physical system. We need a process to do that. It's all about the process. When given a problem as a practicing engineer, the way you solve that problem is you have a process and you start from scratch. You don't think about what problems in the past you've solved that are similar to the problem you face now, as you do typically in any tests that you take in your engineering courses in school. Unfortunately, you take tests, you try to do well in tests, not by following a process, but by thinking about what problems similar to the one you face that you're trying to solve now. And that is wrong. And you come away not learning anything, not having a process that you can depend upon, rely upon, have confidence in as a practicing engineer, so that when you're giving a problem for which it has not been solved by anybody, and there are no similar problems that you can look to solutions of, that you have to solve. That's what innovation is all about. You need a process to solve any problem. When you have a process, you have confidence. When you have a process, you are assured of getting to a solution. So you must learn the process and apply the process. What is that process? It's called the dynamic system investigation process. This diagram here is so important. It's the foundation of modern engineering practice, modeling. But let's describe this process. The process starts with a physical system. The physical system can be an actual physical system, as we have here. We have it built. I can observe its behavior. I may want to improve its behavior, change its behavior. And so I have a physical system that I can make measurements on. Oftentimes, though, we have a concept in the design process that is not built. It only exists in concept in our minds, and we want to be able to predict its behavior before we build it. So these are the two situations that we're often confronted with. The physical system can be a real thing that's already built, or it can be a concept in the design process. The first step is to make simplifying assumptions and to use engineering judgment to create a physical model, an approximation of the physical system that either exists in reality or as a concept in the design process. What simplifying assumptions? Well, they come from engineering judgment, from practice. Here we assume that the disc and the bar are rigid, they're homogeneous. The disc rolls without slipping on the horizontal bar. These are examples of simplifying assumptions. They have to be justified through measurement, if you have the system, or through previous experience, as we will see. So the first step is to apply simplifying assumptions and engineering judgment to the physical system to create an approximation of that physical system, a physical model. Physical model is a picture on paper of the physical system, which is also could be just a concept, that approximates that. The physical model will have parameters, numbers, that need to be identified. This is called parameter identification. We identify model parameters. What are the model parameters here? Well, the mass of the disc, the mass of the bar, the length of the bar, the radius of the disc. These can all be measured. Then you can calculate properties such as where is the mass center? What is the mass moment of inertia? And so we identify model parameters, and so our physical model, which is an approximation of the physical system, now has numbers. What do I do with the physical model? Once I have the physical model, I apply the laws of nature. What are the laws of nature? Maxwell's equations, the Newton-Euler equations of motion, conservation of energy. These are laws of nature. They cannot be proven, but they have never failed in their application or use. They have never been disproved. Here we apply Newton's second law, more formally the Newton-Euler equations of motion to our physical model. Out of that, we get a mathematical model, differential equations, normally ordinary differential equations, but highly nonlinear ordinary differential equations that are often coupled when we have many rigid bodies in our dynamic system. We need to solve these equations. We have Simulink. Simulink can solve any differential equation of any real-world complexity. So it's very important that you can create Simulink diagrams, obtain responses, understand what the Simulink diagram is telling you. But it's also very important that you do hand analysis, because computer simulations, even with Simulink, take time, and often the insight that you need is often clouded. It's not direct, it's not obvious. Sometimes a hand calculation, after you've linearized perhaps the equations of motion, simplify them somewhat so you can do a hand solution, will give you insight, very quick insight that using Simulink and running numerous simulations may not even become apparent. So we solve equations both analytically and numerically. The result is the solution of the differential equations, the predicted motion. Whatever we ask our simulation to do, whatever we want it to predict. Maybe we want it to predict what the oscillation frequency is, what the normal force of the disk on the horizontal bar is as the motion proceeds, what the friction force is. Is the no-slip approximation valid? It requires a certain friction force in order for the no-slip approximation to be valid. Once we predict behavior, we then need to compare it to reality. Because numerical simulation, or the solution of these differential equations, without validating them through measurements, is at best questionable and at worst useless. And so if we have the system, we measure the system. We perform experiments, we use our measurement analysis techniques to then compare the predictions to the experiments. What happens if you don't have the real system and can't do experiments on it? What happens if the physical system that you start with is a concept in the design process? What do? Well, you have to rely on past experience and experiments in order to validate maybe not the entire physical model and mathematical model, but maybe parts of it that are questionable, that you may have some doubts on. But you must compare your predictions to measurements, either of the existing system or to measurements made on past systems. You might even have to build a portion of your concept in order to understand a certain aspect of the concept's behavior. But experimental modeling and analysis and prediction without experimental verification is at best questionable and at worst useless. Once you have this comparison, if the comparison is good, well, then you can think about, do I need to improve this system? Do I need to change the system in any way, either its parameters or maybe the concept or configuration? And you can do that by just changing your physical system, either in reality or in concept, and going through the modeling process again. But if the comparison is not adequate, what do? Well, most likely you have to go back and look at your physical model and your simplifying assumptions and see what might be lacking, what might be incorrect. Or you need to go back and check your measurements, your measurement techniques, or the measurements you're using from past experience to see if they actually apply. But once you have a physical model of a physical system that either exists or is a concept, you have everything. It's all about the process. Engineers need a process to solve new problems. That's innovation. If you have a process, you have power. If you have process, this engineering and system investigation process, you can solve anything with confidence. So this is your new approach to solving engineering problems, all engineering problems, not just in dynamics, in fluid mechanics, in thermodynamics, in heat transfer, in machine design, in any of your mechanical engineering subjects. This is the process you follow. Before we start to solve our plane motion dynamics problem, we need to understand some fundamental concepts of rigid body dynamics, and in particular, plane motion. These are concepts that perhaps you've learned in the past and forgotten, but they're essential concepts that you need to know in order to apply the engineering system investigation process to this rigid body plane motion situation. The first is that dynamics is made up of two separate topics, kinematics and kinetics. The kinematics, which always must be done, comes first. The kinetics then follows. Kinetics is the geometry of motion. It describes the motion of bodies without reference to the forces which either cause the motion or are generated as a result of the motion. It's used to relate position, velocity, acceleration, and time without reference to the cause of the motion. So we're talking about rectilinear or curvilinear translation, position, velocity, acceleration, or angular position, velocity, and acceleration. But it's all about geometry. There are no forces and no torques. The forces and torques, of course, cause the motion, or if the motion is prescribed, the forces and torques result from the motion. But we don't consider forces and torques in kinematics. It's all geometry. And in fact, it's almost all algebra, something you learned in high school, something that is essential, even more important than calculus in engineering practice. Algebra, trigonometry, not calculus. Computer programs like Simulink take care of all of our integration and differentiation needs. We need to understand physically what an integral is and what a derivative is, but do we actually perform those operations? Most times not. They're done using MATLAB and Simulink. But algebra, trigonometry, yes, you use those every day as a practicing engineer. Be proficient. Kinetics is the study of the relation existing among the forces acting on the body, the mass distribution of the body, and the motion of the body. So there are forces and torques acting on the body. The mass distribution can be specified by where is the center of mass and what are the mass moments of inertia of that body with respect to some axis through a point on the body. That's called the mass moment of inertia. And lastly, the motion of the body, as described by the kinematics. So it's the relation among those three things that kinetics deals with. We use kinetics to predict the motion caused by given forces. Forces and torques cause the motion. What is that motion? That's forward kinetics. That's your standard dynamics problem. Inverse dynamics, in a sense, is much more important because we usually specify the motion we desire. In a robotic manipulator, we know what the end effector needs to do. We know what the motion is. What forces or torques at the point of actuation need to be applied to our robotic manipulator in order to make that end effector motion happen. This is called inverse kinetics. It's how we pick actuators, how we size motors, how we size transmission systems. This is inverse kinetics. Forward kinetics and inverse kinetics are essential, and we use Simulink to perform our forward and inverse kinetics using the nonlinear model, in this case of our rigid body plane motion system. There is only one reference frame for which Newton's laws, the Euler-Newton laws of nature, are valid, and that's called the absolute frame of reference. But before we define that, what is a frame of reference? Well, it's an XYZ coordinate system that is attached to a body. So any rigid body in this case has a reference frame, an XYZ coordinate system rigidly attached. We say body fixed coordinate system. That's a reference frame. So our disc bar system has a reference frame attached to it. However, when we apply the Newton-Euler equations, we need acceleration of that rigid body, acceleration of its mass center, acceleration of certain points on the body, in order to analyze it, but that acceleration must be what we call absolute. So what do we mean by absolute? Well, space is the geometric region occupied by bodies. Position in space is determined relative to some geometric reference system by means of linear and angular measurements. The basic frame of reference, the perspective from which observations are made, for the laws of Newtonian mechanics, which is what we're using, the Newton-Euler equations, it's called the primary inertial system. It's an imaginary set of rectangular axes assumed to have no translation or rotation in space. Well, where are these axes? They can't be attached to the surface of the Earth because the Earth rotates and translates in space. So these axes are somewhere off in space that are fixed, do not move, do not accelerate. So this primary inertial system is fictitious, and for space travel needs to be an inertial system that doesn't translate or rotate in space. But for us here on Earth, an XYZ coordinate system attached to the surface of the Earth, we will consider to be that inertial system that doesn't translate or rotate in space. Because for the systems that we deal with, the machines that we deal with, the rotation and translation of Earth does not come into use, or it doesn't have to be considered. We consider the surface of the Earth to be ground, fixed. If you're building the SpaceX rockets that need to land on a platform in the ocean within 10 feet of its target, well then certainly the translation and rotation of the Earth will have major effects on the motion of that space rocket. And so your primary inertial system is not the surface of the Earth, but it might be the sun. So you have to understand what a reference frame is, and that we use a primary inertial system to make measurements that we use in our Newton-Euler equations of motion. Also understand that measurements show that the laws of Newtonian mechanics, they're valid for this reference frame as long as any velocities involved are negligible compared with the speed of light, 186,000 miles per second. Measurements made with respect to this reference system are said to be absolute. Well, nothing moves at the speed of light except on the atomic scale, the microscopic scale. What we're dealing with are objects on the macroscopic scale. So our laws of Newtonian mechanics are valid for the macroscopic scale, the macroscopic problems that we deal with. And our primary inertial reference system will be the surface of the Earth because we're building machines that operate on the surface of the Earth. Know that for any kind of satellite, space travel, launching of rockets, the inertial system is not one attached to the surface of the Earth, but needs to be someplace farther out, attached to the sun, attached to a fixed star. Since the universe is all in motion, this primary inertial system is a fictitious inertial system that we prescribe to use to make our analysis and predictions useful, valid. We throw the terms particle and rigid body around quite often without a good understanding of what we mean by those terms. A particle, from your physics training, is a body of negligible dimensions, but it also can represent a rigid body whose dimensions are irrelevant to the description of its motion or the action of the forces acting on it. The body may be treated as a particle. It can also be defined as a rigid body that does not change its orientation, it only translates. If I'm trying to analyze the motion of an airplane as it flies from New York to Los Angeles, and if I'm only interested in the flight trajectory, its path from New York to Los Angeles, and I do not care about its roll, pitch, and yaw, its attitude as it moves from New York to Los Angeles, but I'm only interested in the path of its center of mass and not its orientation, I can treat the airplane as a particle. So I'm not interested in its change in orientation. I'm only interested in its translation. So a particle is not only something that's very small, it can be a rigid body for which we're only interested in its translation and not its rotation, not its change in orientation. Well, then what then is a rigid body? Well, we all know bodies are flexible. There's nothing that is perfectly rigid. The desk that your computer is resting on is not rigid. It's a flex. Maybe you can't see it, you can't sense it. It might be difficult to measure, but nevertheless, it is elastic. So a rigid body is a body whose changes in shape are negligible compared with the overall dimensions of the body or with the changes in position of the body as a whole. If you're not interested in these changes in shape, then you treat the body as if it were rigid, which is an idealization. When we assume a rigid body, we're assuming that the fact that it can change shape is not important in our analysis. So this is a simplifying assumption. Know the difference between a particle and a rigid body. So a particle can be a rigid body that is moving, whose orientation and changes in orientation are of no interest to us. Then that rigid body can be treated using particle mechanics. We don't analyze particles. We don't care about trajectories of particles, not as an engineer. But when a rigid body can behave as a particle, then what you learned about particle motion becomes then directly applicable. Mass, center of mass, mass moment of inertia. When I ask students to define these three terms, I often get very confusing answers that show the person does not understand at all what they mean. These are essential concepts in rigid body dynamics. Mass. Mass is the quantitative measure of the inertia, which is the resistance to change in motion of a body. It is also the property which gives rise to gravitational attraction and acceleration. In Newtonian mechanics, mass is a constant. So it's a property of a rigid body. It's a property that is constant. It's a measure of the resistance of the body to changes in motion. That's what inertia is. If a body is very, very large, has a large mass, it is difficult to move it from a state of rest. And once it's moving, it's difficult to stop it from moving. It resists change in motion. That's mass. It's distributed throughout the body. It's constant. What is center of mass? The location of the center of mass of any rigid body is a property of the body itself. So it does not depend on the dynamic situation, the axes you use. It's a property of the body, independent of all that. It's independent of orientation or the forces acting on the body. Its position vector with respect to some reference point is given by the following expression, which will apply in the case study at hand. So it's a property of the body. It doesn't matter what axes you use, what forces are acting on it, what its motion is. This is a point in the body that we identify for analysis purposes. It's called the center of mass, given by this equation. What's the mass moment of inertia? The mass moment of inertia of a rigid body is a constant property of the body, and it's a measure of the radial distribution of the body's mass with respect to an axis through some point. So it's a property of the body. It has nothing to do with the forces acting on the body, the torques acting on the body, the motion of the body. It has everything to do with its mass distribution. And when you ask someone what is the mass moment of inertia of the body, you have to give them two pieces of information in order to get an answer. Mass moment of inertia with respect to what point in the body, mass moment of inertia with respect to what axis through that point in the body. If you don't give those two pieces of information, then you can't determine what the mass moment of inertia is. So it represents the body's resistance to change in angular momentum about the axis through the point. The point can be on or off the body, and the axis orientation through the point and the point need to be specified to calculate the mass moment of inertia, which can be calculated using this formula. We can calculate the mass moment of inertia of rigid bodies, but oftentimes we model rigid bodies as being made up of standard shapes: bars, discs, spheres, cylinders, for which the mass moments of inertia with respect to certain points in the body and certain axes through those points are given in tables. So while we need to have the ability to calculate the mass moment of inertia of a rigid body at a particular point for a particular axis through that point, most times we use tables to determine the mass moments of inertia that we need for analysis purposes. So you need to understand for a rigid body what is the mass of the rigid body, where is the center of mass, that point in the body where if you collapsed all of the mass to that single point, the motion of that point is what is needed to analyze the motion of that rigid body. So it's that point which tells us how that rigid body is going to move, how it's going to translate. The mass moment of inertia, again, is a property of the body, independent of axes used, independent of forces or torques applied. And it has a mass moment of inertia for every point in the body and for every axis through that point. What you need to specify is what point and what axis. What do you need for your analysis? And we will apply these three concepts in the solution of our rigid body plane motion problem. Two other concepts are force and moment. They're both vectors. Force is the vector action of one body on another. There are only two types of forces in Newtonian mechanics. You will have to draw a free body diagram of the rigid body or system of rigid bodies that you're analyzing. In that free body diagram, you will show forces and torques acting on the body. There are only two types: forces or torques that act at a distance, and these are gravitational or electromagnetic. These are the only two that you need to consider. We do not consider the nuclear forces, atomic forces. We're dealing with macroscopic, large-scale dynamics problems. The only other forces that exist then are contact forces. No contact, no force. So see where the rigid body contacts its environment, and there will be forces at that point of contact. no contact, no force. Centrifugal force, Coriolis force, these are fictitious forces. They're not real. You will understand this as we proceed. So the only forces you need to consider in drawing a free body diagram are gravitational and electromagnetic. Here in our problem, the only force at a distance is gravity, the weight. And then contact forces. Where does the body, the rigid body that you've removed from its environment and drawn a picture of for your free body diagram, where does it contact its environment? If you have contact, there's a force. No contact, no force. And then moment. The moment of a vector about a point O in space is a vector that is equal to the cross product of the vector from any point O to any point P on the line of action of the vector and the vector. So this line from point O to point P, which is a point on the line of action of the vector, we want to find the moment of this force vector about point O. The moment is independent of the choice of point P on the line of action. The point P can move up and down the line of action because, as you'll see, this angle phi will change. And so the moment is given by the vector equation R cross F. It's a cross product. The magnitude of R cross F is the magnitude of R, the magnitude of F, the sine of the angle between, the sine of the angle phi. And the direction is given by the right-hand rule. In this case, R cross F by the right-hand rule will give me a vector coming out of the page perpendicular to the page. We need to determine moments because moments then will cause change of orientation of a rigid body. So these are two very important concepts that you need to understand how to determine what forces are acting on your free body diagram, and then be able to calculate moments of forces about specific points on or off the body. Coordinate. The coordinate is a quantity which specifies position. Any convenient measure of displacement can be used as a coordinate. X, Y, Z, angles usually identified by Greek letters like theta or phi. So we use coordinates to specify position. Degrees of freedom. The degrees of freedom of a rigid body is the number of independent coordinates needed to completely describe the motion of a mechanical system. It's characteristic of the system and does not depend upon the chosen set of coordinates. So for here, our mechanical system consists of the disk and bar. The question we ask then is, how many coordinates do I need to completely specify the motion of that system at any time? If I have many rigid bodies in my system, how many coordinates do I need to completely specify all the elements of my mechanical system at any instant in time? This is independent of any coordinate system chosen. It's a property of the system itself. In this case, our bar and disk rigid body is put into a situation where it moves, oscillates on the horizontal bar. The question then is, to answer the question, how many degrees of freedom does this system have? You need to then ask yourself the question, because you can't answer that question just directly by looking at the system and saying, oh, this has 1 degree of freedom or 3 degrees of freedom. You have to ask yourself the question that underlies this question. So when I ask someone how many degrees of freedom does a system have, I'm really asking then, or the person needs to ask themselves, how many degrees of freedom, or what is the number of independent coordinates that I need to completely describe the motion of the system at any time? A rigid body in rectilinear translation has one coordinate, 1 degree of freedom. It moves in a straight line. If it moves on a curve in a plane, it has 2 degrees of freedom, x and y, if it translates in curvilinear motion. If it moves on a plane where it can translate in any direction, but can also rotate about the z-axis perpendicular to that plane, it has 3 degrees of freedom, an x, a y, and a theta. A rigid body in space has 6 degrees of freedom. So the jump from plane motion to three-dimensional motion is not just adding another degree of freedom, it's doubling the number of degrees of freedom, doubling the number of coordinates needed to completely specify the motion of a system. The world is not flat. The world is three-dimensional. Engineers need to understand three-dimensional motion, how to analyze three-dimensional systems, how to build a Tesla, an automobile, how to build a SpaceX rocket. These are three-dimensional systems. How to build a Harley-Davidson motorcycle. However, in machines that are made up of mechanisms, mostly these machines and the mechanisms that comprise them are plane motion mechanisms. That's why plane motion is such an important aspect of dynamics. But please don't misunderstand. As engineers, as mechanical engineers, you need to understand three-dimensional motion and three-dimensional dynamic analysis. That's not the subject that we're dealing with here. You first need to understand plane motion, and then the same process that we use here with additional understanding, additional skills, analysis skills, but the same process will get you to an answer no matter whether you have 1 degree of freedom translation or 6 degree of freedom rigid body motion. Lastly, constraint. Constraint is a limitation to motion. If the number of coordinates is greater than the number of degrees of freedom, there must be enough equations of constraint to make up the difference. It doesn't, so if you're using the right number of coordinates, the same as the number of degrees of freedom, there will be no constraint equations. The constraints will be already considered and included in your choice of coordinates. But if you choose to use more coordinates than there are degrees of freedom, the difference is made up by equations of constraint. For example, imagine a simple pendulum, which you know from physics. A simple pendulum that oscillates back and forth in a plane. A bar with a steel bob at the end of it that simply oscillates back and forth. It's a 1 degree of freedom system. You use theta, the angle of the bar of the pendulum with respect to the vertical, as it oscillates back and forth in the plane. It's a 1 degree of freedom system. Could you use the x and y coordinates of the bob at the end of the pendulum to describe its motion? Of course you could. But just because you're using x and y coordinates, the number of degrees of freedom is still 1. Those two coordinates, x and y coordinates, are not independent. They're related by the rigid length of the bar. So you can use any coordinates you want, but if the number of coordinates you're using is greater than the number of degrees of freedom, then you will have equations of constraint to make up the difference. We've talked about reference frames a little bit. We have to talk about notation. Notation and reference frames go hand in hand. Engineers have a certain language that they use that is universal, that all engineers throughout the world can understand. If you don't use this language, then what your work can be misunderstood, misinterpreted. And in the world we live in today, where work takes place 24 hours, 7 days a week around the world, and engineers work with engineers throughout the world, You're often not at your work to explain what you've done. The work has to stand on its own, be complete, understandable by any engineer using the language of engineering. Hence, we talk about notation, and it goes hand in hand with reference frames. A reference frame is a perspective from which observations are made regarding the motion of a system. So we've talked about the primary inertial reference system, reference frame. A reference frame is simply an XYZ coordinate system fixed to the body, a body-fixed set of axes. A moving body, such as an automobile or airplane, frequently provides a useful reference frame for our observations of motion. When you're on an airplane or in an automobile and you're making observations with respect to that automobile or airplane, with respect to an XYZ coordinate system fixed to that automobile or airplane. Even when we are not moving, it is often easier to describe the motion of a point by reference to a moving object. This is the case for many common machines, such as linkages. So every rigid body will have a reference frame, an XYZ coordinate system rigidly attached to it. And we need to then understand its motion, right, with respect to other reference frames on other moving bodies or with respect to ground. So an engineer needs to be able to correlate observations of position, velocity, and acceleration of points on moving bodies, as well as the angular velocities and angular accelerations of those moving bodies from both fixed and moving reference frames. So depending on your reference frame, that will determine what you observe, what the answers are when you ask, what is the velocity of an object? Translational, angular. What is the acceleration? Translational, angular. Depends on the reference frame that you're observing the motion in. Of course, all accelerations need to be determined with respect to the inertial reference frame, which for us will be a reference frame fixed to the ground, the surface of the earth. Here we see a simple dynamic system. Consists of a rigid support, which we will call ground. It's attached to some object that's attached to the floor in some laboratory. So it's our grounded reference frame, which I call R. So the R reference frame is a ground reference frame that has an XYZ axis attached to it in any orientation I want, to whatever point I want, but it's fixed to ground. To this grounded reference frame, I have a shaft here that rotates. It rotates about this axis that I show as the x-axis. So it rotates as shown with this angular velocity, which is called omega 1. This has an XYZ coordinate system attached to it, and it moves with the rigid body, which is in fixed axis rotation. Its reference frame, the shaft, is identified as R1 with coordinate system x1, y1, z1. Now attached to the end of the shaft is a disc, which can rotate as shown about this z-axis. It rotates with an angular velocity here called omega 2. It has an XYZ coordinate system attached to it, and it's called x2, y2, z2, as this body number 2 has reference frame R2. So I have three reference frames in this problem: R, R1, R2, each with a fixed set of XYZ axes. If I ask the question, what is the acceleration of point P, this point on the disk, it's meaningless. What is the angular velocity of R1, as shown here? It's meaningless. What is the angular velocity of R2? It's meaningless. because the acceleration of P as viewed from where? If I'm riding on the disk, point P doesn't move. If I'm on the shaft looking at point P, it has a certain acceleration. If I'm on the ground looking at point P, it has a different acceleration. So where you're observing the point, where you're observing the body from, has to be specified. The angular velocity of the shaft with respect to what? With respect to R, with respect to R2, where are you observing this angular velocity? The angular velocity of the disk, which we call omega 2. The angular velocity as viewed from where? R1 as viewed from R. So this notation is useless and meaningless. The proper notation is the acceleration of P with respect to an observer in the R reference frame. The angular velocity of R1 with respect to the R reference frame. The angular velocity of R2 with respect to R1, as shown here. This is the proper notation. You have to specify even when it is obvious, as it is here. We have one rigid body, we have one ground. So we have the rigid body fixed reference frame, the body fixed axes, and then the grounded reference frame. So it's obvious what we're talking about when we talk about angular velocity or acceleration of a point on the body. It's with respect to ground. But you still must use the proper notation, because quickly, when you have more complicated situations, if you're not in practice of using the proper notation, you'll use incomplete notation, which will lead to misunderstanding and errors in the analysis. We attach unit vectors to our XYZ coordinates. So as you can see here, when I talk about the XYZ coordinate system and the X1, Y1, Z1 coordinate system, one has what we call simple angular motion with respect to the other. The shaft is rotating about this x-axis, which doesn't change in orientation with respect to ground or with respect to R1. It's shown here with this angle alpha, and the matrix relationship between the unit vectors in the R reference frame and the unit vectors in the R1 reference frame are shown here. If you don't understand this matrix equation, go back, review your mathematics, your trigonometry, and make sure you understand where this relationship comes from. If I now look at the relationship between R1 and R2, the unit vectors in the R1 reference frame, the unit vectors in the R2 reference frame, the angle phi is what separates the two, as one is in simple angular motion with respect to the other. The disk rotates about this z-axis, which is fixed in R1. The matrix representation is shown here. Again, if you don't understand this, please go back to your mathematics training to understand this relationship in using trigonometry and the fundamentals of matrix representation. But notation, proper notation is essential, even in the simplest problems. You need to get into the practice of proper notation. Otherwise, it will lead to errors, misinterpretation, because you will not always be there to answer questions or explain your work on paper. Right? There are instances where simple errors in notation, in units, lead to catastrophes and loss of time, millions of dollars of money, and most importantly, lives. We're discussing rigid body plane motion. What do we mean by plane motion? Motion that happens in a plane, as I show here. You have a block sitting on the plane. The block can move in the x direction, can move in the y direction, can rotate about a z-axis perpendicular to this plane of motion. 3 degrees of freedom. If the block simply translates in the x direction, it's 1 degree of freedom. If it translates along some curve in the plane, 2 degrees of freedom, as it has x and y components. That's translation without change in orientation. If it keeps its same orientation as it moves, then it's simple translation. But if the block rotates, changes its orientation, then it has a 3rd degree of freedom, rotation about the vertical z-axis perpendicular to this plane of motion. If I were to drive a stake through this block and allow it to rotate about that axis, it couldn't translate in the x or y directions. It could only rotate. We call that fixed axis rotation, 1 degree of freedom. But what do we mean by plane motion? Well, there are 3 attributes of a plane motion system. There's no such thing as a pure plane motion system. As you saw, the rigid body and the discs are not all in one plane. The disc and the bars rather, there are 2 bars, one in the front, one in the back, that are not in the plane of motion, but are there to make the motion be able to be modeled as plane motion. So there are no forces out of the plane of motion. So the plane of motion must contain the mass center of our rigid body. And as you saw in the picture, we must have mass symmetry with respect to that plane of motion. So the plane of motion is the XY plane, the plane of the picture, going through the mass center of my disc and bar system. So you have the same mass on one side of that plane as you do on the other. The mass distribution is the same. That's what we mean by mass symmetry. So the center of mass is located in that plane of motion. And I have symmetry with respect to that plane of motion. And any forces act in the plane of motion, and they're projected onto the plane of motion. So there are no forces that are perpendicular to that plane of motion that would cause it to move out of that plane of motion. And if there are forces that exist out of the plane of motion or perpendicular to it, I neglect them for analysis purposes as they are insignificant for my analysis. Let me give you an example of a plane motion problem that is not a real plane motion problem. You will learn about mechanisms, and the most widely used mechanism in the world is the 4-bar mechanism. We have a ground, we have link 2, link 3, link 4. Links 2 and 4 are connected to ground. They are in fixed axis rotation. Link 3 is in what we call general plane motion. Looking at this, you would consider this to be a plane motion problem. The mass center of the system or the mass center of the links is in the plane of motion. All the forces are acting in the plane of motion. There's mass symmetry with respect to the plane of motion. However, when you build this and look at its side view, you see that all of the links cannot be in the same plane of motion because they'll bang into each other. They need to be separated by bearings with short axles that cause the system to look like this. So from the side view, there is no plane, identifiable plane of motion. There is a plane, an imaginary plane shown here in this picture that the linkage moves in for analysis purposes. But here you see in reality, there is no plane motion. And so there will be forces, torques that act out of the plane of motion. So the observation we make is that these joints at O, at A, at B, and at M cannot transmit any moments in the Z direction as they rotate freely, neglecting friction. So here we have pure rotation about axes perpendicular to the plane of motion at O, at A, at B, and at M. These are revolute joints. However, these joints can transmit reaction moments in the X and Y directions. So if the mechanism is out of balance or there are disturbing forces, these joints can resist those forces, resist those moments in the X and Y directions. This is what we call partial three-dimensionality. You need to consider this to properly select the bearings, the ball bearings at the joints so they don't fail. However, this requires three-dimensional dynamic analysis, which, as practicing engineers, you'll have to consider and invest time in study to understand. But for now, we're neglecting that. So we're neglecting the physical situation and considering this plane motion idealization, knowing that when you build the actual system, there could be out-of-plane forces and torques that result, that the bearings will need to withstand, and so must be chosen accordingly so they don't fail. Here you see a picture of our bar disc system, and you clearly see the two bars, one on the front, one on the back, appended to the disc, rigidly attached to the disc, so that the disc can actually roll on the horizontal bar, move without tipping in or out of the plane of motion or twisting on the bar. So this is for application purposes, and when we model this as a disc, rigid and homogeneous, with a bar that has the mass of the whole assembly here, both bars with the connecting pin at the bottom. This mass M includes both bars, and we show it here in plane motion. And again, this bar M, the red bar, is rigidly attached to the blue disc. This bar has a length L, and whether you consider the length to be from end to end, from this pivot to a comparable point at the end, is really not of any consequence, where, again, this analysis is not exact. It has some approximations, so we need to have the approximate length of this bar from end to end, and forget about the hole in the bar because of the screw, the pivot point, or the rigidly attached point where I have a screw here that screws the bar rigidly to the disc. So our simplifying assumptions are rigid bodies, homogeneous bodies, and plane motion. But also I assume no slip here at the point of contact between the disc and the horizontal bar. What do we mean by no slip? No slip simply means that at the point of contact between the disc and the bar, there are actually 2 points there. One, the point of contact on the ground, and the point of contact on the disc. So those 2 points of contact must have the same velocity in order to have no slip, and also must have the same tangential acceleration in order to have no slip. And that's velocity and tangential acceleration as viewed from any reference frame, but they have to be the same. Otherwise, you have slip. Why is the no slip condition an important condition to recognize? Well, it's important because then the rotational motion of the disc and the translational motion of the disc are related. They're coupled together. When you have a wheel rolling on the ground without slip, the motion, horizontal motion of the geometric center of the wheel and the angular motion of the wheel are related. So it's a 1 degree of freedom system. The horizontal motion of the geometric center of the wheel and the angular motion of the wheel are related through the no-slip condition. Imagine a bowling ball thrown down the lane that is well oiled. You have slip. The bowling ball translates down the lane. Oftentimes it's rotating backwards. How is that possible? Or it's rotating with a side spin. The only time you get no slip in the interaction between the bowling ball and the lane is when you reach the end of the lane and there's no oil and the bowling ball grabs the lane. You have no slip, and that's why the ball then suddenly turns, and if thrown properly will hit the pocket of the pins and knock them down. But before that, there's slip. Of course there's slip. There's oil on the lane that causes the slip, and the ball is moving with no relationship between translation and rotation. To determine these parameters, I simply weigh the disc, I weigh the bar, I measure the radius of the disc, I measure the length of the bar, and they're given here, and these are the numbers that we will use. So with that introductory information, here is your formal assignment. Perform a complete dynamic system investigation of this physical system following the following steps. Describe the actual physical system which is located in the mechatronics studio. The physical system exists. I actually have it in my office for you to observe. Physical modeling. Use engineering judgment and make simplifying assumptions. For example, no slip between the disc and the horizontal bar. About the behavior of the physical system. List each simplifying assumption, the justification for the simplifying assumption, and the mathematical simplification that results. Represent the physical model with a well-labeled diagram. Two very important points. You must list your simplifying assumptions. Your analysis is based on your simplifying assumptions. If the person reading your analysis doesn't understand what assumptions you made, the analysis could be meaningless. And it's the assumptions that you make that will lead to the validity or invalidity of your analysis. Making the wrong assumptions will lead to a worthless conclusion. Making the right assumptions will lead to a model whose predictive capability is invaluable. Also, a well-labeled diagram. Diagrams without axes labeled, without annotation, without a title, without a description of what the diagram is for and what it shows. These diagrams are useless. Model parameter identification. For the physical parameters in your physical model, state the procedure to determine the numerical value for each parameter. Calculation, reference book, experiment. List the values of the parameters provided for the actual physical system. Here we have the mass of the disc, the mass of the bar, the length of the bar, the radius of the disc. Properties like mass center, mass moments of inertia will be calculated, or tables will be used to identify what those are. But those are not physical parameters. These are parameters. Those are parameters that we then calculate from the measurable physical parameters. Mathematical model. State the appropriate laws of nature. Here it's the Newton-Euler rigid body equations for plane motion. Laws of nature, Maxwell's equations, conservation of energy, conservation of mass, and so on. Here it's the Newton-Euler rigid body equations of motion for plane motion. And we apply them to the physical model to create the mathematical model of the system, the differential equation of motion. The mathematical model is the mathematical model of the physical model. And the physical model is an approximation of the physical system. When we solve the equations to predict the behavior of the system, we're predicting the behavior of the physical model, not the physical system. Comment on the nature of the differential equation of motion. They will be, if there are more than one, most likely they'll be coupled, but almost always they will be nonlinear, solvable using MATLAB Simulink. Dynamic behavior prediction. Draw a simulation block diagram on paper by hand to graphically represent the mathematical equation of motion. Why do we draw the simulation block diagram by hand? We do it so we know that we get an understanding of the complexity of the mathematical model. We understand what blocks we will need when we build the actual Simulink diagram. We can lay out the blocks on paper to understand the physical space that we need to create the simulation diagram. We do this by hand so that when we go into MATLAB Simulink to create the simulation diagram, we can select the blocks that we need, we can lay them out in appropriate positions on the computer screen without waste of time and a resulting cluttered diagram. As you check, you should be able to write the equation of motion directly from the block diagram. Once you have the equation of motion, in this case we have one nonlinear ordinary differential equation. Once we have that differential equation, the equation of motion, the question then is, does the simulation diagram represent that equation of motion? That is a question you can always have an answer to, because a check on your simulation diagram is to write the equation of motion from the simulation diagram. You always can test that, and if you get the same answer, get the same differential equation that you started with, then your simulation diagram is correct. It accurately represents the equation of motion. The equation of motion may be wrong, but your simulation diagram accurately represents it. So there is never a reason for an incorrect Simulink diagram in any problem that you solve. Using numerical values provided for the physical model parameters, create that MATLAB Simulink block diagram to solve the nonlinear equation of motion. Then we run a simulation to predict the system response to an initial displacement from equilibrium. We give the system a non-zero initial condition. We offset the bar from the vertical, its stable equilibrium position, and release it. So this system is not being driven by an externally applied force or torque. It's being driven by a non-zero initial condition, which gives it stored potential energy, which then is released and is converted into kinetic energy of motion. Predict the natural frequency of the system for small oscillations. The video of the actual system shows the natural frequency for small oscillations to be 1.37 hertz. Why do we say small oscillations? Well, we can have large oscillations, and the Simulink diagram will accurately predict the response because it's a nonlinear simulation. However, if we want to use hand calculations and linearize our equation of motion, we do this for small oscillations. So the approximation that the sine of the angle is approximately equal to the angle, and the cosine of the angle is approximately equal to 1. When the equilibrium condition is at 0 degrees, then we can do hand calculations, and from hand calculations predict approximately what the natural frequency of small oscillations is for the system. The Simulink diagram will do this even for larger angles, larger initial conditions, larger angles of oscillation. However, to apply that to a physical system might be difficult because it's hard to put the system into an oscillation with a large initial angular displacement, as any slight inaccuracy or any slight twist in the application of that initial condition will result in the disk moving in and out of the plane and falling off the horizontal bar. So physically applying the initial condition is easier when that angle is small. And it tells us how our model then will accurately predict the behavior of the system. I don't need large oscillations to do that, large angle oscillations to do that. Validation of the no-slip assumption, of all the assumptions that we make: rigid bodies, homogeneous, plane motion. The no-slip assumption is the most questionable one. So we need to use a Simulink diagram created to predict the normal force and friction force between the disk and the horizontal support bar. There has to be enough friction to support the no-slip condition. The friction between the steel disk and the steel horizontal bar is represented by a coefficient of static friction, which is a system property, steel on steel. We can look up values of the static and kinetic coefficients of friction for steel on steel. So that is the friction that is obtainable when you have steel on steel. The coefficient of friction is the ratio between the friction force and the normal force at that point of contact. From my simulation, I can determine what that ratio is, what the coefficient of friction needs to be throughout its motion to support the no-slip condition. If that coefficient of friction then is less than or equal to the actual friction available in steel-on-steel contact, my no-slip condition has been validated. However, if that's not the case, then I need to revisit my analysis, relax the no-slip assumption, in which case the rotational motion of the disk is not related to the translational motion of the disk. I have a 2-degree of freedom system. I need a coordinate to describe the translation of the disk, x, and an angle theta to describe the rotational motion of the disk. It's a 2-degree of freedom system. The no-slip condition would not hold. And the easiest way to analyze that would be just to treat the system as if it had no horizontal friction. This would be a limiting case of not enough friction, but it would give us some insight into the behavior of the system or what the frequency of oscillation would be if the no-slip condition is not valid. Lastly, we compare prediction with actual behavior. Computer simulation without experimental verification is at best questionable and at worst useless. Compare the dynamic behavior predictions to the actual behavior observed. We see in the video, and I've determined what that observed natural frequency of oscillation is using a stopwatch and a visual observation. Comment on the validity of those predictions and of the simplifying assumptions used. State any changes you recommend for the physical model if necessary. This is a complete dynamic system investigation. Ingrain this in your mind, in your memory. Use it whenever you have a dynamic system to analyze. All of your systems are dynamic systems, whether they're electrical, mechanical, electromagnetic, mechanical, fluid, thermal, it doesn't matter. This is your dynamic system investigation process. Here I show a sketch, my physical model of my physical system in 2 different configurations. The first is the static equilibrium configuration or position. I show the disk with its radius, its geometric center, its center of mass, which is at the geometric center since the disk is homogeneous. The bar, which has the mass of, again, the front and back bars, so I consider it to be 1 bar, with a length L, and its center of mass at its geometric center since it is homogeneous. And I show it in a static equilibrium configuration. If I put this system on this horizontal bar, this support, which I show dashed because the horizontal bar is not part of my physical model, I remove the physical model from the environment and show it on my diagram, so the environment is shown dashed. This would be the static equilibrium position. The system would remain stationary if put into this position. There's nothing to make it move. No non-zero initial conditions, no forces or torques that will cause it to move. I identify a coordinate system, a right-handed coordinate system. X to the right, Y down. Gravity is acting down. This is a vertical system. The Z-axis is into the page, and if I curl my fingers from X to Y, that is the positive direction for rotation, with my thumb pointing in the Z direction, which is into the page. However, we start all of our analysis by putting the system into a displaced position, a non-equilibrium position. So here I show the system displaced by an angle theta. Everything else remains the same, but this is the diagram that I use for analysis purposes. My rigid body has been put into a displaced position, a non-equilibrium position, and this is what I use for my free body diagram, and as you will see, for the effect diagram. I also identify the point of contact C on both diagrams. That's an important point because that is where I make the assumption of no slip. The first thing I need to do is identify the mass properties of my rigid body. That includes the center of mass and also the mass moments of inertia. I assume that the disk and bar are homogeneous, therefore the locations of the centers of mass are at the geometric centers, point O, and also at the geometric center of the bar, which I showed on the previous diagram. The composite center of mass is located as follows. If I want to know what the center of mass is for the composite body, I proceed as follows. Using my X and Y coordinate system with an origin at point O, with the X-axis to the right and the Y-axis vertical, I know that the center of mass by symmetry has to be located on the Y-axis because I have a same amount of mass on the, again, the YZ plane to the positive X direction as I do from the YZ plane in the negative X direction. I have mass symmetry. So the center of mass has to be located on this Y-axis. Hence, X bar is equal to 0. My equation that locates the X coordinate of the center of mass is the total mass times the location of the X coordinate of the center of mass, and that equals the individual masses times their X coordinates of their individual centers of mass, which are 0. For the Y coordinate, I apply the same equation. The total mass times the Y coordinate of the center of mass equals what? The location of the center of mass for the bar, which is at the midpoint, L over 2, times its mass, plus the Y location of the disk with respect to my coordinate system X and Y, which is at 0 because I located the X and Y coordinate system at O, located the origin there, so its coordinate is 0. If I solve this, I find Y bar is equal to 0.197 L, or using the measured value of L, 0.0290 meters from point O along the bar. That's the mass center for the composite body. Let's consider mass moments of inertia. For the disk, I'd like to know the mass moment of inertia of the disk with respect to its center of mass for an axis in the z direction. So it's a z-axis through the center of mass of the disk. If I look at a table, I can find for a homogeneous disk, that mass moment of inertia is given by 1/2 m, its mass, times its radius squared, which results in this number. The units are kilogram meter squared for mass moments of inertia. For the bar, the mass moment of inertia with respect to its center of mass and an axis in the z direction through that center of mass is given in the table as 1/12 ml squared. Substituting in values, I get this number, kilogram meter squared. I'd like to know what the mass moment of inertia is with respect to the center of mass of the composite body and a z-axis through that center of mass of the composite body. I use my parallel axis theorem and I transfer the mass moments of inertia of the disk and bar with respect to their centers of mass and the z-axis through those centers of mass to the center of mass of the composite body. The parallel axis theorem says take I bar disk and add the product of the mass times the square of the distance between the two parallel axes, 0.197 L squared. If I do that for the bar, it's the mass moment of inertia of the bar with respect to its own center of mass and the z-axis through that point, plus m times the distance between the two axes, the z-axis through the composite center of mass and the z-axis through the center of mass of the bar, which is L over 2 minus 0.197 L, and I square that. Plugging in the numbers for the L, M, small m, large M, and capital R, I get this result, 0.00385 kilogram meter squared for the mass moment of inertia of my composite body about a z-axis perpendicular to the plane of motion through the center of mass of the composite body. Once we consider the mass distribution, we then move on to kinematics, the geometry of motion. If I look at the angular motion of this rigid body, we call this simple angular motion. The reason we call it simple angular motion is because the z-axis of the grounded reference frame and the z-axis of the body fixed axes do not change orientation during the motion. It's simple angular motion. Simple angular motion is described by an angle. Simple angular velocity is described by the time derivative of that angle. Simple angular acceleration is defined by the second derivative of that angle. This is simple angular motion that we have here. The z-axis of the grounded reference frame and the z-axis of the body fixed XYZ coordinate system stay parallel during the motion. That's simple angular motion. The angular motion is described by an angle, the velocity by the derivative of that angle, the acceleration by the second derivative of that angle with respect to time. And that's what I show here. Notice that I show the complete notation, the angular velocity of R1 in the R reference frame, the angular acceleration of R1 in the R reference frame. Right? These are vectors. These are the scalar magnitudes. The vectors is in the z direction. It's perpendicular to the plane of motion. That's the direction for the angular velocity and the direction for the angular acceleration. So my reference frames are the grounded reference frame, which I show here, x and y, with an origin at the geometric center at this instant in time. And my body fixed axes, as shown with the system in a displaced configuration, you see the body fixed axes are x1 and y1. And the angle between the two is the angle theta. The z-axis of the xy coordinate system is into the page. The z-axis of the x1, y1 coordinate system is into the page and parallel to the xy coordinate system z-axis. The z-axes of the two reference frames remain parallel during the motion. I have simple angular motion, hence the simple angular velocity and angular acceleration representations. And the relationship between the xy and x1, y1 coordinates and I hat, j hat, and I1 hat, j1 hat unit vectors attached to those coordinate systems are given by these matrices. Verify for yourself that these matrix representations are correct. The trigonometry is correct. The MATLAB, the matrix representation is correct. Note, angular velocity and angular acceleration in three-dimensional motion is not simple. It's not simple either in representation or concept, and requires detailed mathematical analysis. In three-dimensional motion, angular velocity and angular acceleration are not the rates of change of any one angle. But here we're dealing with a plane motion problem for which we have simple angular motion, and so the analysis is simple. Let's now talk about the velocity and acceleration of a point in space with respect to two different reference frames. The solution of nearly every problem in dynamics requires the formulation of expressions for velocities and accelerations of points of a system under consideration. Here we use full vector analysis. In your study of plane motion problems, maybe you only use scalar analysis and did not use full vector analysis techniques. While in plane motion problems, scalar analysis can work and can give you correct answers and can give you insight, the world is not flat, it's three-dimensional. SpaceX rockets, Tesla cars, Harley-Davidson motorcycles, high-speed maglev trains are all three-dimensional systems. In order to analyze their dynamic behavior, you need full three-dimensional vector analysis techniques. To not learn them confines you to living in a flat world and to jobs that essentially exist in a flat world. The justification for plane motion is that most machines use mechanisms. Machines are made up of mechanisms that are, for the most part, plane motion mechanisms. Four-bar linkages, multi-bar linkages, slider cranks are all plane motion mechanisms that combine to form machines that are plane motion machines. And these can be handled well by scalar analysis techniques. But you need to be able to use full vector analysis to handle three-dimensional systems, and the world is full of those types of systems, and the engineering applications that are three-dimensional in nature are numerous. So let me explain to you the expressions for the velocity and acceleration of a point P with respect to two different reference frames, one grounded and one moving. If you don't understand these equations, you need to go back to your dynamics course and review the derivation of these equations. My job here is not to derive these equations, but to use these equations. And I will show the use of these in our plane motion system to show the ease of use. And of course, you get the same answers as you do in scalar analysis. I have a grounded reference frame R. This is my inertial reference frame attached to the ground. There's a point P that I want to understand the motion of, and I need its absolute velocity and absolute acceleration. So the velocity and acceleration of P with respect to ground. There's also a moving reference frame, a moving rigid body that perhaps I'm located on, with a reference frame x1, y1, z1. These are body fixed axes, and I observe the motion of particle P. But what I need in order to do a dynamic analysis is not the velocity and the acceleration of p with respect to me in the r1 reference frame moving with the x1, y1, z1 axes, but the velocity and the acceleration of p with respect to r, the grounded inertial reference frame. So what these equations say are, in the first equation, the velocity of p with respect to the grounded reference frame is equal to the velocity of a point on the moving reference frame A with respect to the grounded reference frame, plus the velocity of p with respect to the moving reference frame. First, the velocity of p with respect to the moving reference frame as if p were fixed in the moving reference frame, plus the velocity of p with respect to the moving reference frame. So this term will give you a tangential velocity. This term will give you a relative velocity. If p is not fixed in R1, p can move with respect to R1, and this term is non-zero. The acceleration follows by saying the acceleration of p in the grounded reference frame, which is what we need for our Newton-Euler equations, is the acceleration of A with respect to the grounded reference frame. That's the absolute acceleration of A, plus this expression, which turns out to be what is called centripetal acceleration, and this expression, which is tangential acceleration. This is the acceleration components of P with respect to R1 as if P were fixed in R1. Tangential acceleration, centripetal acceleration. R omega squared, R alpha. However, if P can move with respect to the R1 reference frame, we have two additional terms. One is the acceleration of P with respect to R1, but then we have another term which is completely unexpected, which results from the vector analysis, which is this term, which is 2 times the angular velocity of R1 in R crossed with the velocity of P in R1. So if P can move in R1, there's a velocity of P in R1, which results in an additional acceleration term called Coriolis acceleration. So if P is not fixed in R1, we have these additional terms. If P is fixed in R1, then for velocity you have tangential velocity, for acceleration you have centripetal acceleration and tangential acceleration. We'll apply these equations to our problem, our dynamic system. In that case, the point P, the point in question, the point we're investigating the motion of, will be fixed in the moving reference frame. And so we won't have a velocity of P in R1, an acceleration of P in R1, or a Coriolis acceleration. But this equation is so fundamental and should be applied in simple situations, in complicated situations out of necessity, but just to show yourself that you can apply them, you can manipulate them, you get the same answer that you would get if you applied scalar analysis techniques. Let's now find the absolute accelerations of the disk, the center of mass of the disk, the center of mass of the bar, and the center of mass of the composite body. First of all, we investigate the no-slip condition at point C. I've already described what the no-slip condition means, but here in a diagram it shows that if I have the disk by itself rolling on the ground with no slip, as the disk rolls, its geometric center moves from this position to this position by a distance x. That distance has to be the same distance as this curved portion on the disk that is the same length as the distance between the point C in the initial state and in the final state. So the length of this line is the same as the length of this line, and I have then the no-slip condition. So just from trigonometry, x is equal to the radius r times this angle theta, the no-slip condition. So the velocity of the center of mass, x dot, is r theta dot. The acceleration of the center of mass, x double dot, is r theta double dot. Once I have this, I can then proceed. So by inspection, without vector analysis, I can write the acceleration of the center of mass of the disk with respect to the grounded reference frame is simply x double dot times I hat, the unit vector in the x direction, which equals r theta double dot I hat. The acceleration of the center of mass of the bar in the r reference frame has two components. Well, it has three. It has the component of the center of mass of the disk, because I'm using the expression that the acceleration of the center of mass of the bar is the acceleration of point O with respect to ground, plus the acceleration of the center of mass of the bar with respect to point O, which is a centripetal acceleration and a tangential acceleration. So the acceleration of the center of mass of the bar with respect to ground is r theta double dot I hat, which is the acceleration of point O, minus L over 2 theta dot squared, again, the acceleration in the minus y1 direction, the minus j1 hat direction, equal to L over 2 theta dot squared, minus the tangential direction, which is in the minus x1 direction, L over 2 theta double dot. So that's in the direction this way. This is the acceleration of point O. This is the centripetal acceleration. This is the tangential acceleration. Notice that I have the unit vector I hat, but here I have the unit vectors I1 hat and J1 hat. But you know the relationships among these vectors through matrix analysis and your rotational equations from the previous slides. You can then combine these effectively. Similarly, if I want to know what the acceleration of the mass center of the composite body, instead of using L over 2, I simply use 0.197 L, and the same analysis applies. I strongly urge you to go through this analysis to get the acceleration of the center of mass of the bar with respect to the R reference frame, the grounded reference frame. So if I make use of that equation, I say then this is the acceleration of O with respect to ground. This is the centripetal acceleration. This is the tangential acceleration. This is the relative acceleration. And this is the Coriolis acceleration. Since the center of mass of the bar is fixed to the bar, it's fixed to the R1 reference frame, the acceleration of that center of mass in the R1 reference frame is 0. The velocity of the center of mass in the R1 reference frame is 0 because the center of mass is fixed in the R1 reference frame. So this term is 0 and this term is 0. So the acceleration of O in the R reference frame is just x double dot I hat, which is equal to r theta double dot I hat. The angular velocity of R1 in R, its simple angular velocity, is just theta dot, and it's equal to k hat. It's in these positive z-axis, or theta dot k1 hat. The position vector from O to Gm, the mass center of the bar, is L over 2 J1 hat. So it's permissible to mix unit vectors, but when you take cross products, the unit vectors all have to be in the same reference frame. Notice that k hat and k1 hat are identical because I have plane motion, simple angular motion. The z-axis of the R reference frame and the z-axis of the R1 reference frame are parallel and stay parallel throughout the motion. The angular acceleration of R1 and R is just theta double dot k hat, which is theta double dot k1 hat. Given these expressions, just now perform the vector operations, omega R1 and R cross R from O to the center of mass of the bar. Perform the cross product, you get this result. If you don't know how to do vector cross products with unit vectors, please review your previous mechanics notes. Then we perform this analysis, and we get this result. Then I perform this analysis. Since I have all of the terms represented here, it's just a matter of, as they say, turn the crank and do the analysis, and I get this result. So this is my tangential acceleration, and this is my centripetal acceleration. If I combine these terms, I get the same result as I got by inspection using scalar analysis, and I would get the same result by just replacing the center of mass of the bar with the composite center of mass location. The vector analysis gives us the same result as we got by doing scalar analysis by inspection. Your question then is, why do I need to go through all this vector analysis? Because if you have three-dimensional motion, or if the point that you're interested in is not fixed in that R1 reference frame, in this case, suppose I had a slot in that bar that's attached to the disk, and in the slot I had a mass that would slide within that slot that was perhaps attached to a spring in that slot, then that point P would not be stationary with respect to that moving reference frame, the bar reference frame, and vector analysis would be needed to perform that analysis, even though that's only plane motion. Still is plane motion, but still vector analysis will ensure that you get the correct result. And it will certainly, if you insist on using scalar analysis techniques, it will certainly validate the correctness of your scalar analysis techniques. When performing engineering analysis, you always want to have, if possible, two ways to get an answer. You don't want to rely on one answer to build something for which failure could cost lives. So if you can have more than one way of determining an engineering result, either by dynamic analysis using Newton-Euler, or as you will learn in the future, using the Lagrange method, which is an energy method, two ways to determine equations of motion, two ways to get an answer to an engineering problem, the more confidence you'll have in your answer. You'll be asked to solve problems for which there are no solutions. There's no solutions manual. You can't go check your answer when you work as a practicing engineer. You don't get credit for a correct answer. It's not about grade. It's about designing a system that works and that is safe, will solve problems and protect people. We've considered mass distribution. We've done our work in kinematics. Now it's time to move to kinetics. When we analyze a system, in this case a plane motion system, we first draw a free body diagram. On the free body diagram, we show the body removed from its environment. We free the body from its environment. We draw it on a piece of paper. We show dash the environment, the boundaries of the body with its environment, to show the location of the interactions that may be happening. We free the body from its environment. We show the forces and torques acting on the body, which can only be two kinds: those that act at a distance, gravitational and electromagnetic, and contact. No contact, no force. We show the location of the center of mass, and this is our free body diagram. We then show on an effect diagram the terms that are contained on the right side of our equations of motion from our Newton-Euler laws of nature. Those equations say the summation of forces in the x direction is equal to the mass times the absolute acceleration of the center of mass in the x direction. Summation of forces in the y direction is equal to the mass times the absolute acceleration of the center of mass in the y direction. summation of moments about the center of mass is equal to the mass moment of inertia about the z-axis, the perpendicular axis, through that center of mass times the absolute angular acceleration. And this representation gives us a flexibility to pick any other point P, in this case shown here, about which to sum moments. Now, often these two diagrams are combined where these terms on the right-hand side of our equations of motion are shown on the free body diagram. And they're shown dashed and in the opposite directions that they're shown on the effect diagram. This is called the D'Alembert approach, and it consists of a free body diagram that has not only the forces that act at a distance and the contact forces, but it has what we call the inertia forces and the inertia torques. They're shown on the free body diagram dashed to show that they're not real, they're fictitious, and they're shown opposite to the positive direction that would be shown on the effect diagram. That's called the D'Alembert diagram, the D'Alembert approach. The diagram tends to get a little bit too cluttered, but if you feel that is what you're confident in or comfortable doing, please use that approach. I prefer the free body diagram, effect diagram approach, because whatever I do on the free body diagram, I then do on the effect diagram, and I get a complete equivalence of the two. So here's my free body diagram of my bar disc system shown in its displaced configuration. I show the acceleration due to gravity. I show my weights, which are the only forces that act at a distance. There are no electromagnetic forces. My contact force is only with the ground. I have a normal force and a friction force. The normal force is obviously upward. The friction force could be left or right. I don't know. Pick a direction. If the answer in your analysis is minus, you know the direction is in the opposite to shown on the free body diagram. I do some geometry here, which you can verify. Geometry is just the geometry that shows the relationship between G and O and the angle theta and these perpendicular distances that I need for my moment equations. On the effect diagram, I show the right sides of my equations, my Newton-Euler equations. I show my inertia torques, one for the disk and one for the bar. I show the absolute acceleration of the center of mass of the disk. I show the absolute acceleration components of the center of mass of the bar, m r theta double dot, centripetal acceleration, tangential acceleration. I'm making use of the no-slip condition at point C, so x equals r times theta. Once I've done this, then everything that follows is just, as they say, turning the crank. Whatever I do on the free body diagram, I do on the effect diagram. I can sum forces in any direction. I can sum moments about any point. Whatever I do here, I must do here. And this geometry will help me in taking those moments. If I want the equation of motion, I want an equation that does not contain any unknown forces or torques. Since the only unknown forces are the friction force and the normal force, if I sum moments about point C, those forces will not enter into my equation, in which case the resulting equation will be the equation of motion that will describe the motion of the system. If I want to know what the friction force and normal force are as the system goes through its motion, I then need to write equations, either force equations or moment equations, that have those forces in them. So a summation of forces in the x direction will contain the force of friction. Summation of forces in the y direction will contain the normal force, and so I can solve for each of those forces independently, and we will do that. On the free body diagram, if I sum moments about point C, I get this expression. You should make sure that you can take moments about a point of forces on a free body diagram. That's elementary knowledge, elementary experience from dynamics, make sure that you can do that. I need to do the same thing on the effect diagram. If I take moments about point C, I have my two inertia torques, and then I have the moments of m r theta double dot, capital M r theta double dot, small m r theta double dot, and then the components of my tangential acceleration and centripetal acceleration. If I combine all these together and simplify, I get my equation of motion. Notice that there are no unknown forces in this equation. It's a nonlinear ordinary differential equation. Nonlinear because I have a cosine, theta dot squared, and a sine term. Highly nonlinear, can only be solved using MATLAB Simulink numerically, cannot be solved analytically by any technique. So this is what we will draw a Simulink block diagram for to determine the motion of our system. Suppose instead of using the centers of mass of the disk and the bar separately, I chose to use the composite center of mass to do my analysis. I've redrawn my free body diagram and effect diagram. The free body diagram just shows one weight force, which is small m plus rm times g, at the composite center of mass. I still have the friction force and normal force. On my effect diagram, I only have what? I have the acceleration of the center of mass of the composite center of mass equals to m plus m r theta double dot. And then I have the centripetal acceleration and tangential acceleration terms. So we see a little less, fewer terms, but a little more complicated terms than in using the separate centers of mass of the disk and the bar. Either approach is valid. It's a sort of a toss-up as to what you want to do. In order to use the composite center of mass, you first have to find the location of the composite center of mass. Again, I've shown the geometry here that we need for these distances. If I sum moments about C on the free body diagram, I get this expression. If I sum moments about C on the effect diagram, I get this expression. Notice that I have the mass moment of inertia of the composite body about its center of mass, which we solved earlier, which needs to be calculated in order to use the composite center of mass as my reference for this analysis. So either approach is valid. Verify that you understand where these terms come from. If I then combine the equations from the free body diagram and the effect diagram, and I do analysis, simplification, just combining terms, just straight algebra, I get this expression. Now I need to compare this to the previous equation to make sure I get the same result. Rather than going through a lot of algebra, I'll just substitute in numbers. Normally we don't want to do that because if I substitute in numbers and then the numbers change, I then have to redo the calculation. The longer we can retain the variable representation of our equation of motion without substituting numbers, the better off we are, because we can then see the relationships among different terms, and we can also then, if we change parameter values, we don't have many more calculations to perform. So I'm sort of violating a practice, but I'm doing that to compare two equations in the sort of the fastest way possible. So I'll substitute in values for my parameters for small m, for large m, and for L and for R to make this comparison. So my equation, when I treat the masses separately, I get this equation again with numerical values. If I treat the system as a composite mass and evaluate substituting in numerical values, I get the identical expression. So both approaches are valid. Again, I'm substituting in numerical values only for comparison purposes here to make sure the equations are identical, rather than showing by algebra the equivalence of some complicated algebraic expression. Numerically, I show that they are identical. I now want to solve for the friction forces and the normal forces. The easiest way to do that is on the free body diagram, sum the forces in the x direction, which is simply minus the force of friction, summation of the forces in the y direction, which is the normal force, minus the weight term. And then on the effect diagram, simply sum all of the fictitious forces, the inertia forces in the x direction, and the inertia forces in the y direction, and you get two equations of motion. And again, I've simplified both of those equations through just algebra. And so I have an equation for the friction force and the normal force. We know when two surfaces are in contact and you have Coulomb friction, dry friction, the system parameter, the system characteristic, is the coefficient of static friction. There's also a coefficient of kinetic friction when we actually have slipping motion between two surfaces, but here we have no slip, we're using static friction, and you see that the coefficient of static friction is equal to the ratio of the friction force to the normal force. From material properties of steel on steel, as the coefficient of friction is not a material property, it's a system property. One material on another, the range of values for steel on steel is 0.5 to 0.8. So as long as the coefficient of friction needed for the no-slip condition is less than these values, my no-slip assumption is valid. If the coefficient of friction needed for the no-slip condition to be valid is greater than these values, that value is not available from the steel-on-steel condition, and I will have slip. To continue with the practice of substituting in numbers, which I've done here just for simplicity and also for comparison purposes, I now have my equations for the friction force and the normal force. If I use the same approach on the composite free body diagram, effect diagram, I get the equation for the friction force, the equation for the normal force. If I substitute in numerical values for small m, large M, capital R, and L, capital R and L, I get these two equations, and they are identical. So now I have equations. I have the equation of motion, and I have an equation for the friction force, and I have an equation for the normal force, and all three equations are highly nonlinear, which I will now solve using MATLAB Simulink. Here I've summarized my system equations. The first equation is the equation of motion. It only contains theta double dot, the angular acceleration, and no unknown forces or torques. This will describe the motion of the system. Then I have an equation for the friction force and an equation for the normal force. I've left the equations substituting values for the parameters. It's not something that I recommend you do. Always keep the parameter values as variables because if they do change, you only then need to change them in one location, which would be a MATLAB M file. And then that change will propagate throughout all of the equations and all of your simulation diagrams. I'm doing it here but just for expediency and to make the diagram a little less complex. I expect you to follow the rule of not including any numerical values in your Simulink diagram, except numerical values that are part of the equation themselves. We don't include parameter values in our Simulink diagram. We let the parameter values propagate into our simulation diagram from the MATLAB M file. So I have three equations, and I want to now generate a simulation diagram for these three equations. I have my two integrators. This line represents theta double dot integrated once with an initial condition on angular velocity, which is 0, will give me theta dot. Integrated again with an initial condition on angular position specified in radians, nominally for small oscillations less than 15 degrees, but we express it in radians, will give me theta. My first equation says that theta double dot equals what? Equals the product of 1 over this term here, which is the inverse of 0.00858 minus 0.00407 cosine of the input. The input is theta. So 1 over that times the sum of these two terms. The terms come in with minus signs. So it's minus the product of theta dot squared times 0.00204 times the sine of theta. The other term is 0.393 times the sine of theta. That gives me theta double dot. And I put it to a scope so I can look at the response. My friction force here, as shown with the scope, is equal to the sum of two terms. It's equal to the sum of 0.0702 minus 0.0400 times the cosine of theta, which is the input, times what? Times theta double dot, which is this term right here. And the other term, which comes in with again, a minus sign, is with a minus sign, which is 0.0400 times the sine of theta. The input is theta, which you see from this line, times what? Times theta dot squared. So the input here is this term right here is theta dot squared. The sum of those two with a minus sign gives me the positive friction force. If I do the same thing now with the normal force is given in this scope, and it's equal to the sum of three terms. First, the constant term, 13.557. Then this term here, minus 0.0400 times the sine of the input, which is theta. And that's multiplied by theta double dot, which is given by this signal here. And then the other term is minus 0.0400 times the cosine of the input, which is theta. And that gets multiplied by theta dot squared, which is this term right here. So the sum of these three terms gives me n. This is my Simulink diagram. I verified that the Simulink diagram is correct by writing the equations of motion from the Simulink diagram. If my equations here are correct, then the simulation diagram is correct, and there's no reason why you should ever have an incorrect simulation diagram. Here is the first scope. It's the theta scope. It shows the oscillations of my system in response to an initial condition, which is given in radians. This is theta in radians. This is approximately 15 degrees as my initial displacement, represented in radians. I see the oscillations. The oscillations do not decay. I haven't modeled anything that would cause the oscillations to decay. The friction force for the no-slip condition does not do any work. And so the friction force, if it's rolling without slipping, will not cause the oscillations to decay. Of course, there's air resistance that will cause the oscillations to eventually stop, but we haven't modeled that, and so we won't see that effect. If I count the number of oscillations in a certain amount of time, I can get the frequency, which is shown to be 1.47 hertz cycles per second. Here's the second scope, which shows the friction force. This is in newtons, SI units. We see the friction force varies from a positive, a little bit greater than 0.6, to a negative value of minus 0.6. And again, it's consistent throughout the number of oscillations over the 10 seconds. It is a sine wave variation between those two extreme values at the same frequency of the variation of theta, same frequency of oscillation. This is our friction force result from our simulation diagram. The last scope is the normal force acting on our disk bar system, the normal force between the ground and the disk, N, which is shown here. And it varies between between a little bit greater than 13.75 newtons and minus 13.35 newtons. So it varies between a little bit greater than 13.3, a little bit less than 13.8 newtons. But we notice the oscillation is twice the frequency of the oscillation because the normal force, as it goes through an oscillation, goes through 2 cycles of variation between extreme values. You can see this from the simulation itself. So we notice that the normal force here is changing at twice the frequency of the oscillation, and it changes in a sinusoidal way between these two values, 13.3 and 13.8 newtons. Lastly, I combine the friction force and the normal force to then calculate the coefficient of static friction, which is the ratio of the friction force to the normal force, and over the range of motion during the oscillations, the coefficient of static friction needed for the no-slip condition is between approximately 0.05 and minus 0.05. So in magnitude, it's 0.05, which is much, much less than the steel-on-steel coefficient of static friction. So the friction coefficient that's necessary to ensure the no-slip condition, rolling without slipping, is much, much less than what is available. And so my no-slip condition, rolling without slipping, has been validated. The last question we need to address is the question that if we have slipping, no rolling, but pure slipping, will the frequency of oscillation be less or greater than the frequency of oscillation observed in the no-slip condition? Well, we certainly could take the approach where we go through the analysis all over again and let the coefficient, let the friction force be 0, and then determine the frequency of oscillation. However, if the friction force is 0 and we have a slip condition, the system then becomes a 2-degree of freedom system because x and theta, the motion of the geometric center of the disk, and the angular motion of the disk are no longer related by the relationship x equals r times theta. X and theta are now decoupled, are not dependent on each other. The analysis becomes much more involved. You have now 2 equations, one for x and one for theta, in addition to the equation for the normal force, and the friction force we're assuming to be 0. But there's a more insightful way to answer our question. If I asked you to do the analysis of a simple bar pinned to a pivot that is frictionless, and I asked it to oscillate back and forth about this pivot point, and I asked you to do the dynamic analysis to calculate what the natural frequency is in hertz of the oscillation, your analysis would show that the frequency is approximately equal to, for small oscillations, 1 over 2 pi, the square root of m, the mass, times g, times L over 2, where L is the length of the bar, divided by the mass moment of inertia of the bar with respect to the pivot, which from a table you would find is equal to 1/3 ml squared. So we see that the frequency of oscillation is inversely proportional to the square root of the mass moment of inertia with respect to the pivot point. Now, I know where the composite center of mass is for my system. and I show here a G, and I show the calculation again that we performed earlier when talking about mass distribution. Now, for the no-slip condition, the disc and bar rotates approximately about point C. For the slip condition, where the friction force is 0, the disc and bar rotates approximately about G. If I determine the mass moment of inertia with respect to each point, I get the following result. Using the parallel axis theorem, I can transfer the mass moments of inertia of the disk about its geometric center and the bar about its geometric center to G. And I've done that here. I can also, using the parallel axis theorem, transfer the mass moment inertia of the disk about its geometric center to point C, and the mass moment of inertia of the bar about its mass center to point C using the parallel axis theorem. If I do that, I get this expression. So what do I note? I note that the mass moment of inertia of my composite system with respect to C is greater than the mass moment of inertia of the composite system with respect to its mass center. So since the mass moment of inertia of the composite system with respect to its mass center is less than the mass moment of inertia of the composite system with respect to the contact point with the ground C, the frequency of oscillation for the rolling case will be less than the frequency of oscillation for the sliding case. So if I have slip, I would expect the frequency of oscillation to be slightly higher than the frequency of oscillation that I observe in the rolling case. Here's an example of using understanding and insight to answer a question without just mindlessly going back and letting the friction force be 0 and going through all the analysis again. I can answer this question very insightfully, very directly, very accurately by using my understanding of how these systems behave, how this system behaves, either in slipping or in rolling. That concludes the presentation here of the case study. I thank you for your attention, and I urge you to study this case study thoroughly, as it is most important that you know how to follow a process to solve a rigid body plane motion problem. Thank you.